Okay, so we also call it as a real correlation. So it refers to a problem when we have correlation between current error and the other errors. Meaning that within the errors they have different values of error, they have relationship. So the one we call as serial correlation. So autocorrelation is systematic pattern of the errors or residuals. So residuals is the estimate of the error or disturbance. So the true error we call as the disturbance. But when we estimate based on the sample, so we get estimate y minus y hat. That one we get the residual. That one we call residual, which is estimate for the disturbance. So error or residual, whether it's positive or negative autocorrelation. So in a systematic pattern of errors or residual, whether it's positive or negative correlation, meaning that whether between error or residual they have a positive relationship or negative relationship. So we have positive autocorrelation, and we also can have what we call as negative autocorrelation. So for accurate estimation of prediction, all systematic information has to be included into the regression model. In other words, we must capture a systematic pattern in our model. If it exists, if we do not capture the systematic pattern as part of the model, then the model is considered not complete. So the model is not ready now. So you have to find a solution in order to have your model to be free from autocorrelation. Okay. So or at least you need to make sure that, or you need to find a way so that the estimate of the coefficient or parameter standard error not affected, or we call it not less or not affected by the presence of serial correlation. So basically, the consequence of having the problem similar to the other two, to the previous two problems. So basically, in terms of the estimate, it's still okay, it's still acceptable, the estimate, but the problem is in between. The problem is it gives us the unreliable estimate of the parameter standard error. So that your estimate also not reliable to make or to perform hypothesis testing. So let's say the regression model under our convention is given by this. So we have 2x, one dependent variable y, and then 2x independent variable. So it is the error term. Error term. So the error term represents other factors other than x1 and x2. Remember, so this one we know that y dependent variable not only influenced by x1 and x2, it influenced by many factors. But in our model, we only include x1 and x2. So basically, the error term, it represents the influence of other factors that not included in the model. So x1 other than x1 and x2. So we need one of the requirements of the ordinary least square model. It requires the error terms one to be independent each other. So meaning that each value of, so for each observation, the value of error term for each observation must be independent, not related to the other values of the error term. Each of the values must be random or independent of each other. So meaning that the covariance between different value of error term. So imagine this one, UI represent the observation. You recall that the first lecture we had before. So let's say you have a set of variable, you have number of y observation, number of x observation. So this is the error term. So the error term. So different. This meaning that one of the assumption requires assumption on a least square or ordinary least square requires each value of this one error term for different observation to be independent. So there is no correlation or relationship between any of these and other error, any error and other error within the errors. Yeah. So it requires the covariance between different different error. So U and ij not the same, meaning that I and j represent the position. So this one maybe, for example, the first observation y1, second observation y2. So I. So I and j meaning that different observation. Okay, different observation. So for example, between U1 and U2, U1 and U3 and so on. Okay, between different error, U1 and U2, U1 and U3, U1 and U4 and so on. So there is no, the least square requires, there is no covariance between them, so that there is no correlation. So covariance you divide by standard deviation. You recall the covariance between x and y, and the correlation between x, y. When you divide covariance between x and y over the standard deviation of x, and then the standard deviation of y, you get correlation. So basically covariance can be used to calculate the correlation. So if covariance 0, then correlation also 0. If covariance 0, correlation also 0. So correlation between the two series. So we need our model to have this what we call that this characteristic of the error. So error must be independent, and there is no correlation between different value of different what we call that the error. Okay. So this is what we call as no autocorrelation. But if let's say the covariance, this one covariance equal to 0, but covariance not equal to 0 means that we have correlation. So meaning that different. So meaning that there is a relationship between different value of the error. So we have the covariance not equal to 0. So if not equal to 0, then correlation also not equal to 0. Okay, so in general, autocorrelation occurs when the expected value, so expected value between the two, so I mean it's equivalent to the covariance between the two series. Yeah. So not equal to 0. So for the case of no correlation, we need our error. We know that the error term here, the error term. So the error term here can be positive, can be negative. But the average must be 0. The average must be 0. So for each observation, the value can be positive, can be negative. So this for the case of the least square requires the model to have the error to be random. So it can be positive, can be negative, but it's random. Each of these to be independent or random. So each of these is not affected by other value of error. Okay. So this is what we call as no correlation. So there is no correlation in the model. However, if we have something like this, meaning that the current value of error positively influence the next value of error. So this one, current value and next value. So the first observation, the current value positively influence the value of error for the next one. And then we have positive autocorrelation. So in general, so it positively influence. So if we have negative something like this, means that the current value of error negatively influence the next value of error. So we have positive autocorrelation and negative. So we want our model to have this kind of error. So if we have this kind of positive and negative, then we have to do something because it is the present of positive or negative autocorrelation will make our estimate to be the estimate of the standard error just like before to be incorrect. So that when you perform testing, then it will produce unreliable result of hypothesis testing. So in terms of the order of autocorrelation, if let's say the error only has a relationship with the previous one, the current and the previous one. So normally we have the problem when we use times data. So using annual data, for example, monthly or quarterly data, then it's possible that you have this one, especially when you have data that has trending. So it has trend, then most likely you problems of autocorrelation. So if the error, the error related to the previous one, the previous error, the previous what we call that period, okay, of error, and then we have first order autocorrelation. See if the current error related to the last two errors, and then we have second order. So similarly, we have if the current error related to the last three, then we have the third order autocorrelation. So normally we just, we will treat the first order as AR1. So autoregressive model of order 1, because this one related to the previous one. So if second order is AR2, so third order is AR3, autoregressive order P. So the implication of having autocorrelation problem, the coefficient estimate derived using ordinary least square are still linear and biased, but they are inefficient. So it's still linear and biased, and then just like the previous two problems. So meaning that the average of all possible estimate is equal to the true value of parameter, but they are inefficient. So they do not have minimum variance compared to the procedure that take into account autocorrelation. In short, ordinary square estimator are not best linear and biased estimator. The estimated variance, the variance of ordinary square estimator are biased. So although the estimate of the parameters are unbiased, but the estimate of the variance are biased. So the estimate of the variance of the estimator. Okay. And sometimes the usual formula to compute the variances and standard error of ordinary square estimators seriously underestimate true variances and standard error, thereby impacting the t-values. So this gives the appearance that the particular coefficient is different from 0, whereas in fact that might not be the case. Therefore, the utility and the accuracy are not really reliable. So normally, so you better be careful. So you have a data, you have a set of data. So y and x, for example, when you regress, and then it produces significance. So that significant estimate of the coefficient is possible that it's because of the autocorrelation, represent of autocorrelation. So you make conclusion that there is significant influence of x on y, but basically it's not. But the result shows that it's significant, but it is because of the autocorrelation. So the usual formula to compute the error variance, namely, so this one, the error variance that normally we calculate using the sum square of error divided by the graph freedom n minus k minus 1. So the residual sum of square divided over the degree of freedom, it is a biased estimator of the true regression error variance, and in some cases it is likely to underestimate the true variance. So as a consequence, the conventionally computed R square may be unreliable measure of the R square. So meaning that if you want to conduct hypothesis testing, then it's important for you to remedy the problem. Okay, otherwise you will make conclusion based on the unreliable value of standard error, the regression variance or regression the standard error of the estimator. So to detect autocorrelation problem, so we can either identify based by looking at the graph or graphical inspection, or you also can later we have more formal tests, okay, numerical tests. So let's say we consider this model. So the residual give estimate for the true error. So what we can do that you after you estimate, you get the residual, okay, and then you can produce graph. So you can expect you produce plot of the residuals against time, just like before. And you see whether it has any pattern of this. If random, okay lah. Okay, but if you have something like this or other than this, and then you have problem of autocorrelation. So we need the model to have this kind of error, random error. Or you also can plot against the previous value of, just like scatter plot. So scatter plot, You produce scatter plot, your x-axis the previous value of error, your y-axis the current value, and you see if there is any pattern of relationship between previous error and current error. Scatter plot. Formal test for autocorrection. So we have two. The big version, t-test. That is a test for the first order autocorrection by assuming that residual follow AR1 process. So the big version can be used to test the present of the first order. This one, the first order. Okay, it can only be used to detect or to examine or to identify if there is first order correlation. The first order correlation means that the current error influenced by the previous error from the previous period. Okay, you have annual data last year, error for the last year influence the error for the estimate of for this year. Okay. So for the Wilson test, it is used to test the present of first order or two questions. So it cannot be used to test for the present of higher order of two correlation. And then we have the Brush-Brockway LM test, that is which is the more general test that does not only assume that residuals as ER1 process, and it allows us to test if the residual are ERP process. So this one it can be used for any order, so including order 1, first order. Okay, so the Brush-Brockway LM test can be used for any order of the autocorrelation, but every person can only be used for the first order autocorrelation. So for the case of Brush-Brockway, that can be used for first order, second order, third order, and so on. The big version test. So we are testing. This is what we want to test: whether there is correlation between current error and the previous error. So in this case, we are testing whether the value of rho equal to 0 or not equal to 0. So if equal to 0, there is no first order autocorrelation. If the value of rho not 0, then there is autocorrelation problem depending whether it's negative or positive. Okay, whether positive autocorrelation or negative autocorrelation. So the P-versus the test statistic is calculated using this formula. So meaning that residual, this one residual. So residual, the difference between current and previous residual is squared, and then you sum all of them and then divide by sum square of residual. Okay. So it is a ratio for the sum of squares of the difference between successive residual to the sum of squares of the residual. So I think in this one we are not going to calculate manually now. We can try later on. I mean, it's not that difficult to calculate after you estimate. You can try calculate, but I will not ask you to calculate manually. So you can just use this. You can just get this value from this. Okay. So test size T is approximately related to rho as given by this equation. So the big size T, the one that given by this formula, it is related approximately equal to 2 times of 1 minus rho. So rho this one, 2 times of 1 bracket 1 minus rho. So that when rho equal to 0, so when there is no autocorrelation, the velocity is supposed to be around 2. Okay, this value is statistic. You calculate this one. If there is no autocorrelation, we must send rho equal to 0, then the value of this must be around approximately equal to 2. Okay, equal to 2. So if rho equal to 1, so positive autocorrelation, rho equal to 1, then reversal statistic is around 0. So if this equal to 1, then this approximately equal to 0. And then if there is negative autocorrelation, let's say rho equal to negative 1, then the reversal statistic is approximately equal to 4. So meaning that we need our the reversal to be around 2 in order to to have our model, to have a valid model that is free from the auto correlation problem, we need our W statistic to be around 2. So basically around 2 lah. Sometimes it depends on the sample size as well lah. Sometimes 1.6 already okay. So 1.6 up to 2 something, 2 point. So in order to have the what we call to make a better conclusion, then you have to compare your statistic to the critical value from the table lah. But if you don't have the table, you need to make sure that your model produce the B1 statistic to be around 2 lah. Be around 2. Yeah. So in using this approach or this method of testing, the B1 test, it involves about 4 steps of testing procedure. The first step, estimate the regression model under consideration and obtain the estimated residuals. Second step, compute the test statistic or person. This one, you can compute, but I mean we can get from it induced output lah. So after you estimate, if you estimate using induced, then you can get from the output that the person. No need to calculate manually. And then you compare this, you obtain the DL and the U with critical value from table, the upper point and lower point from the B versus the table, and then you compare the test statistic, the B versus with the L and the U, and make decision and conclusion. Okay. Then the decision rule. So how to make a decision in order to see whether the model suffer auto-correction problem or not. So you have to decide based on this, on these given rules. So if the B versus statistic less than the L, so from table we can get the LU. So from the table, the B versus the table is one. So from the table, we are given, so it provides us the 2 values, the L and the U. So you have to compare the B versus with a statistic to this one. And then, so here we have different columns. Different column, it depends on number of independent variables we have. So if let's say in the model you only have one independent variable, X, only one X, then you should refer to this one, K equal 1. If let's say the model has 2x, x1, x2, then you have to refer to this one. Okay. And then this is sample size. How many observations you have? Let's say you have 10 observations, then you should refer to this one. 10, you should refer to this column. Yeah. So, how to decide, how to make conclusion? If you get your D statistic, the B versus statistic less than the L from table, less than the L from table, then we conclude that there is positive autocorrelation. If your D statistic in between the L and U given by the table, between these two values, between the L and the U, then we say that we don't have enough evidence to make decision. So we don't have, meaning that it's unclear for us to say whether there is autocorrelation or not. So we don't have enough evidence. So we say that no decision can be made. Again, if the value arithmetic in between the L and the U. If the value arithmetic is between the U and 4 minus the U, then you see that there is no autocorrelation problem. Okay, so this one we cannot make decision. So we are unable to decide if in between the L and the U. But if the B was statistic between the U and 4 minus the U, then we conclude that there is no autocorrelation problem. There is no autocorrelation between the residuals, between the error. So if let's say the B was statistic in between 4 minus the U and 4 minus the L, so just like before, this one also we don't have enough evidence to make conclusion. Okay, so we don't have enough evidence to make conclusion. And And then if the beam characteristic greater than 4 minus dl, then we conclude that there is negative autocorrelation. Yeah. So basically, it's easier if you draw something like that. You draw a diagram something like this, and then you identify. You calculate lah. So this one 0, you get your dl du from table, dl du from table, and then you calculate 4 minus du. You calculate 4 minus dl. So from table you only get this one. From table, circle table, we only able to get this dl and du. This one you have to calculate lah. 4 minus du, 4 minus dl. So maximum 4. It's not explain to you. The beam characteristic take value between 0 and 4. And then we need, in order to be free from autocorrelation problem, the beam characteristic must be around 2. Okay, must be. It's supposed to be around 2 lah. In order to help us to make a better decision, instead of saying that it must be around 2, but what value around 2? So it depends on sample size lah. Different sample size determine what's the value of lowest value and highest value around 2 that we can set. So you need to refer to table, in order to help us to decide whether we can say that there is no autocorrelation, or we don't have enough evidence to make a conclusion, or there is positive or negative autocorrelation. Yeah. So condition needed for the beam assert test to be valid, it requires the model must have an intercept. So the model must have intercept, this one. Otherwise we cannot refer to the table lah. So the table, this one, the table was prepared for the case of model that has intercept. So it's no longer true if your model does not have intercept. There is no intercept in the model, then the critical value is no longer valid lah. Yeah. The value of x are non-stochastic, that is their values are fixed in repeated sampling, and this one I already explained before lah. Okay, so one of the assumption for radius square. And then the disturbance are first order correlated R1, higher order are not allowed. I mean we cannot use the beam assert test if there is higher order autocorrelation, or we believe that there is higher order autocorrelation, or we want to test for higher order autocorrelation. So the equation does not contain the lag values of the dependent variable and one of the exponential variable, hence the beam assert this test cannot be used for regression model as given here. So meaning that in the model you have lag of y in the model as your one of the independent variable, that one of the independent variable as your independent variable, then you cannot, again just like we call it, you cannot use this table to get the correct value of the L and the U. So you cannot. So you have to use alternative way lah. Maybe you can use the M test for example. So example of detecting autocorrelation problem. Given data for numbers of weekly hotel reservation Y for the past 20 weeks, then average amount of rainfall in this X1 and the average weekly temperature X2, and the model we are considering this model the multiple regression model. So we have two X1 and X2 that we use to explain the dependent variable Y. So the data are given here. This one example. Like just an example. In this file. So this one, you estimate the model. So you just estimate as usual lah. So quick estimate equation. And your dependent variable y, and then space c, space x1, x2, space x2. Okay, so just click OK, and then if you inspect you go to view actual fitted residual graph. So you see this one, this is the actual, the green one is the fitted value, the y hat. So actual minus y hat gives us the residual. So you see the residual is not random, we need the residual to be random. Okay, residual must be random, just like the example given before lah. We need to be something like this, but so there is positive. I mean, if you get to this graph, it is positive, meaning that the current value positively influence the next one. Okay, so basically positive lah, but this one continuously the error, so the value increase. So in this case, the residual is not random or not independent. So there is correlation within the residual. And then if you go back to the estimation result, just now, estimation result, so you notice that the person very low, 0.59. So less than, substantially less than 2, then it is, it indicates what it present of positive autocorrelation of positive. If substantially greater than 2, then we have negative. Substantially less than 2, positive autocorrelation. But to confirm that, you have to compare. You have to compare with the value from the LU table. So this value the way was statistic. So now for this data we have 20 observations, 20 observation, and then how many independent variables we have? 2. So k equal to 2. K equal to 2. So you refer to the table. K equal to 2. This one. Okay. And then sample size 20. K2 and 20. This one. So this is your DL, this is your DU. Okay, DL 1.1, DU 1.537. So you get your DL, DU. So this one you do not need to draw this one because it's very obvious that your DU wasn't less than DL. Okay. If your W wasn't greater than DU, then you have to calculate. If your DU wasn't greater than DU, then you have to calculate 4 minus DU, 4 minus DL in order to see the W wasn't fall in which region. But this one is less than DL because from the table just now, we have DL 1.1. Your W was statistic 0.59, so it is less than DL. So less than DL, so we conclude there is positive autocorrelation. So you refer to this table, refer to this graph or diagram. And this one. So your D was 0.5. This one 1.1. DL 1.1. Your DL 1.1. So your W was 0.59 around here. So it is positive autocorrelation. Yeah, positive autocorrelation. So conclusion, since here the W was statistic less than the DL, then there is evidence to conclude that regression sample from the first order positive autocorrelation. So here defined for first order only, so we cannot make conclusion for the higher order. Okay, the alternative model, the Barge domain and test. This test can be used to test for higher order autocorrelation and valid for regression that contains lack of dependent variable as one of explanatory variables. So let's say, if you include lack of y as one of the dependent variable, then you can use that for this test. But although you cannot use the V-version, but you can use This LM test. And we want to test, so let's say we consider this model and we want to test for present after order of two question given by this. Meaning that we want to test if the current error related to the last three error. So any one, not necessarily all, but any of these, or all, any of these or all. If when we reject, meaning that the current, there is a relationship between current and any of the last three error. Okay. So the first step of testing procedure, you need to estimate the model first, and then get the residuals. So residuals, and then estimate the probability regression model. So you regress the residual that the estimated, the residual you regress against all independent variables from the original model, and then we include the lag of the residual. If you are testing for the third order, you have to put lag 1, lag 2, lag 3 of the residual. Okay, so lag 1, lag 2, lag 3. And then compute the test statistic based on this formula, sample size minus the order of autocorrection that we are testing, the order. So P is the order lah. So let's say for you are testing for the third order, and your P equal to 3. Okay. And then degree of freedom, so we compare to the critical value from chi-square table. Degree of freedom equal to the order of the autocorrection that we are testing. So n sample size of the original model, P order of autocorrelation. So for this given example, P equal to 3, so we are testing for the third order. R square for regression model of the residual. So R square is one not for the original model, but R square from this, when you regress the residual against all these, X as well as lag of residual. So the step 4, if the test has integrated in the value from table, chi-square table, not the Lewis table, but chi-square table, then we get analysis, analysis and conclude there is serial correlation problem. So when we check analysis, so the current error is being influenced by the previous error, the last three or any of them. Okay. So example, reconsider the given data. So let's say we want to test for second order autocorrection for this model, second order. So what we need to do, you need to estimate the model, get residual, and then estimate another model. You regress the residual obtained from the first model, regress the residual against all X that we have here, and then add the lag 1 and lag 2 of the residual. Because we are testing for second order, so lag 1 and then lag 2. So you are testing the first order, and then you can just put lag 1 of the residual. So after you regress, and then you get the R square, and then you calculate sample size minus the order times the R square, so you get this one. Then you compare to the value from chi-square table. So chi-square table, I think previously, so I don't remember whether we use it before. So chi-square table is one, chi-square table. So 5% is one on second page on 5%. Let's say you perform the test at 5% significant level. So this one 0.05. Degree of freedom just now, testing second order, this one second order. Okay. So 5.991. The critical value. So the test calculated test statistic 20 minus 2, 18 times 0.47. This one. So we get 8.5086. So this one greater than the value from chi-square table. So we reject. Now have this at 5% level, and output there is first order or second order of autocorrelation inside. Okay. Because so either one or both. You can perform the test easily in a views, but it gives slightly different result because they replace the missing value with 0. Okay, I will show you. So this one we perform the test first. Now we estimate this model. We estimate this model first. We re-estimate. So we need to have the error. Okay, in ABUs you can easily get the test result if you go after you estimate this one. So you estimate this one, y space x1 space x2, and then you just go to view, residual, then stick select, serial correction, and test. Okay, so this one you need to specify lag to include. So you are testing what order? So you are testing the first order only, then you put 1. But for example, we are testing for second order, so we put 2 lah. The default number is 2. If you are testing for the third order, then you put 3. Yeah. So this one, okay. So you get the test statistic as well as p-value. So you can just make conclusion based on this now. So p-value 0.01 less than 0.05. Then you reject analysis, conclude that there is autocorrelation within the residual. Now the manual approach, after we estimate this one, after we estimate this model, so we have the residual given here. So we need the manual approach. So we need to regress the residual against all x as well as the lag of residual. Lag 1, lag 2 for this example, for the second order, lag 1 and lag 2. So for this one, let's say we save the residual. So after we estimate this one, we save residual. So after we estimate this, so we get residual. So residual as the one given here. So let's say residual, this one residual. So but that one also given here, receipt. So this one, the receipt is store residual for the last estimated model. So every time we estimate a model, then residual for that model are given here. Okay, receipt. So we need to, in order to avoid, if you use receipt when you estimate model, so there's possibility that it's not the residual for the model that we want to use. So it's possible that after you estimate, it is the residual for the second model. So it's better that we save the 1%. So residual, better you save the residual for the original model. So you go to quick generate series. So let's say you name it as a U, and U equal to receipt. So basically you can just use the residual, but as what we call that, just to avoid the possibility that after we estimate, we use the different or incorrect residual, because again this receipt it store the residual for the last estimated model. So let's say now after we estimate the first model, original model, we want to save that residual, so you can just do like this. So in the series, by equation, so let's say you name that as a U. So U equal to receipt. U equal receipt. Okay. U equal okay, so now we have the residual saved here, receipt. For manual approach, you need to regress this receipt against all x from the original model, and then the lag of residual, because we are testing for the second order, so lag 1 and lag 2. Lag 1, lag 2. Okay, so you go to quick estimate equation. So you have U space C space x1, x2, and then we have leg 1, leg 2 of residual. Leg 1, U bracket minus 1. So leg 2, U bracket minus 2. Okay. So name as equation 1. So this one you get your n minus p, 20 minus 2, so 18, and your r square 0.47 to 6. Okay, so you get that value, you can calculate. You get 8.5 compared to the value from chi-square table, so it's one greater, so you got there is autocorrelation of the exists in the model. But this value is slightly different to the one that produced by you just now. So just now we calculate manually, we get 8.50, 8.5086, but the one that produced by you is 8.55, slightly different. Why? Because it replace the missing value with 0. So missing value, okay, now let one, let's say we, okay, now just show you, if let's say we create another 2 more variables that represent leg 1 and leg 2 of the residual. So let's say quick generate series. Let's say leg 1 of the residual we name as U leg 1, which is equal to U bracket negative 1. So if you want to get the same value, to get the same estimate just like it used, then this is how we can do. But the one that produced or given in Legino is acceptable already. So although it's different, but it's acceptable. The manual approach. But it just produce slightly different value because why? I want to show you. So UL1 equal U bracket negative 1. The one I just use UL1 to represent the residual leg 1. You can use different names up to you. UL1 equal U bracket minus 1. Okay, so you have U1, leg 1 of the residual, you do again quick generate series. Now UL2 equal U minus 2. UL2, the residual leg 2. So to get the residual leg 2, so the residual bracket minus 2. So leg means that previous value, the previous 2 values at time t minus 2. Okay, so if you click this one, we have if you choose U and then press Control and then select U1 and UL1, UL2. U press Control, select history, U, UL1, UL2. So you right click, open as group. Okay, so basically just now when we estimate our model, we regress the u against x1, x2, and then the residual leg 1 is 1, residual leg 2. So we don't have the first two. When we estimate the model, when we estimate the when we perform the estimation manually just now, this one manually. Just now when we estimate this one, we don't have the first two. With the model we exclude the first two because we don't have the value for this one and A. So why ABUs produce different values? Because ABUs replace this and A with 0. Okay, so it says that now when you pre-sample missing value like 0 to set to 0. So you press edit, you see up in A we put 0. Okay, then click again. So instead of A, now we replace all NA with the 0, and then we run again. Model, now equation 1, equation this one. So now we re-estimate this model, and you put instead of U bracket 1, U bracket 2, you put UL1, UL2. UL1 space UL2. Okay, so I just want to show how, just now when we calculate, maybe we get different. If they say you want to get the same estimate, just like how it is produced, and then you have to do the same. You have to replace the missing value with 0. Yeah. But without doing this, the original one, the one already acceptable, but the result maybe might be impossible. Because the values are different. In some cases, maybe you can get different conclusion. So you regress this one. So you get now 20 times this one. No longer n minus p, but original value because we have all 20 observation. 20 times this one. 20 times 0.427698. Then you will get the same value, the one that produced by ABUs. You will get 8.55. Okay. Understand? So either one you want to use algebra, even if you use this one also settable, this one settable. Okay, but it has additional step. It replace all the missing value with 0, and then we regress the model, and you get slightly different value of the test ST and the value. Okay. So if you want to get the same value, then you have to do the same. You have to replace all the NA of missing value with 0. But this one already acceptable. Without doing that, also this one acceptable. Okay. Alright, remedial measures. So if you have the problem of autocorrelation, then our estimate is no longer reliable. Equation 1 is now this one. Although your estimate of the coefficient, the slope parameter is okay, this one still can be used because it's unbiased. It is unbiased. It is still unbiased, so we can use the estimate, but the problem now we have not an unreliable estimate of the error and as well as the and the value. So you want to make hypothesis testing, you have to remedy the problem first before you make conclusion, before you conclude that whether x1 and x2 has significant effects on the y or not. Okay. So we have a number of possible ways that we can use to remedy a problem, but each of these not necessarily able to solve the problem. Okay. So the remedy depends upon what knowledge we have or can assume about the nature of the interdependence in the error terms, consider a two-variable model, for example, given this one, and assume that the error term follow the R1 scheme, which is given by this. So meaning that the current error, it is related or influenced by the previous error. So where the VT here specify the usual ordinary square assumption and the rho is known. Assume that we know the value of rho, but normally we don't know. We can estimate now. So if somehow we can transform the model so that in the transform model the error term is really independent, then applying ordinary square to the transform model will give us the usual best linear unbiased estimator, assuming that the other assumption of classical linear regression model are fulfilled. So to see how we can transform the regression, write the regression with one leg, with a one leg as given here, and then multiply regression by rho on both sides to obtain this, and then subtract the second equation for the first equation to yield this one. Okay, so this is what we call as the vector is square, this one generalized square. Yeah. So this one, original model is one, but we know that UT is not random. UT is R1. UT is R1. So this model is not valid. So we need to do something in order to have we need to transform the model so that the error term in the transform model, it is no autocorrelation. Okay, so it's not the RP, or it just there is no serial correlation in the error. So this one, after you transform using this approach, you are able to see that this our new error term is given by this. So UT minus rho, UT minus 1, and then we know that this equal to BT. So BT equal to UT minus rho, UT1. BT equal UT minus rho, UT minus 1. Okay. So after we transform, this is equal to BT. So now the transform equation has serially uncorrelated error term. Okay, BT is really uncorrelated, but UT is really correlated. BT is serially correlated, but BT is really uncorrelated. So basically, we need to transform the model in order to have the transform model that has the new error term to be free from autocorrelation. So since the error term VT specifies the standard ordinary square assumption, the transform regression equation gives us a model that free from serial correlation. By applying ordinary square, the transform model, the estimator obtained will have the desirable best linear unbiased property. The estimator obtained a called generalized least square, the as estimator. So if rho is unknown, we need to estimate it. One way is to simply set rho equal to 1, which is known as the first difference method. So we need to estimate one. We need to estimate the generalized least square. So this one is the transform equation. But what's the value of rho? So there are a number of different ways that we can use to decide or to set the value of rho. Okay, one of them is to simply set rho equal to 1. So we have this one equal to 1, 1 minus 1, 0, we don't have this one. So this one, current value of x minus just minus the previous value of x. Current value, if you have annual data, so value for this year minus the value for last year. Yeah, it is the first difference. Okay. So set rho equal to 1, which is known as the first difference because it does the current value minus the previous one. Just assume you have annual data, so current value of y this year minus the value of y last year. First difference, this is the first difference. First difference method. So this one we don't have. So this one also take the first difference of x. So you have more x, then you do the same. So x2 also do the same. The first difference of x2. So alternatively, we can estimate rho based on the approximate relationship between the Wilson, D statistic, and rho. This one as explained earlier. the B1 test statistic is approximately equal to this one. So from here we are able to get estimate of rho that is equal to 1 minus the B1 statistic divided by 2. Okay. So the first approach simply set rho into 1. Second, use the estimate the value of rho using the estimated value of the calculated value of the B1 test statistic. Okay. So example. So this one I already provide for this. I provide the commands. I use command for the remedial measures. This one. So let's say we set rho equal to 1, then rho equal to 1. So you just regress for given example. You regress your dependent variable become the first difference of y, and then regress against the first difference of x1, the first difference of x2. Okay. So to save time, you just copy this one, copy this, and then you estimate the model, quick estimate equation. Okay. If let's say we simply set rho equal to 1. Okay, so just copy and paste now. We provide spectrum. I just set rho equal to 1. Then our equation, this one, this equation becomes y minus let one y with value, and then this one we don't have 1 minus 1 here. We don't have this one x minus the previous value of x. So in our example, we have 2x. So x1, x2, then we have another one. So x, the difference between two values are the first difference of x1 and the first difference of x2. So we have this one. We have this. Okay. Name as equation. So you get this. Now the question is whether this is reliable estimate. So you have to test them. You have to check whether there is the problem still exists or not. Okay, so let's say you perform the test using LM test, view, receiver, serial correction LM. Let's say the second order, use the default one. Okay, so this one, okay lah. Slightly greater than 0.5, so acceptable. Okay, so that you can now conclude. You can make conclusion whether x1 and x2 has significant influence on y based on this statistic as well as p value. Okay. So this one alternative because this is just the first difference of x1, the first difference of x2. You can use alternative way. You can simply type d1 the first difference of y, dx1 the first difference of x2, dx1 the first difference of x1, dx2 the first difference of x2. It will produce the same result. So d1, dx1, dx2. So you will get the same result. Okay. The second, the next one, if we set, so this one we will statistic around now to something. So previous 0.59. So now if we manage to increase to something, to 1.5. The next, if let's say we use the B1 statistic, to estimate rho, so using the given formula, so 1 minus the d divided by 2, so get 0.7, 0.70345, and use this to estimate our GLS model. So GLS model is given earlier lah. So GLS model this one. So YT minus 0.7 something, YT minus 1. So this one Y minus 1 minus 0.7 something, and so on. So this one X1 minus 0.75, X1 leg 1, and leg 1 of X1, and then we have another one. X2 minus 0.75 of the previous value of X2. Okay. So if we estimate based on the dual statistic, then we get this one. Our GLS question. So just copy this one. So this one a bit tedious lah. So I just show you. Although in practice it's not the proper way of, but you can. This is one of the possible way to remedy the problem. Yeah. There is other easier way. For example, that can be you can try, just like the use of different functional form using double log model, for example, or you can just add other variable. Okay, later we will do that. So this one, second approach, if you estimate O using the minimum statistic, using the value of the minimum statistic, and then you get this. You use that value to estimate this GLS equation. Okay. So this one, the new method 2.15, the new version 2.15, so better than the earlier one. So whether or not you can conclude based on this, then you have to test. Okay, so you have to test serial correlation. Let's say the leg 2, and okay lah, this one. Sorry, this one, second one. Okay, the test I speak, the t value 0.1, so greater than 3.1. So we do not reject. So conclude there is no more autocorrelation, so that you can make conclusion or have a hypothesis based on that transform equation. The next approach, this one, the next approach to estimate the rho. So we have what we call as the using the correlation curve, but this one is it's quite tedious to do. It is useful if you don't have it used, meaning that you estimate using Excel, for example, then you can use this one, but it's no longer relevant for us now because we have a better way to estimate. You can easily estimate using software, computer software. This one we need to iteratively. So this one just for your knowledge, so I will not ask you to do in test or exam. So this one just for your knowledge that we have one possible way that can help us to get more accurate estimate of rho. The previous one we simply set equal to 1. This one we simply set rho equal to 1. And then this one we estimate based on the universal statistic. This one, it allows us, the correlation procedure allows us to get more accurate estimate of rho. But it's quite tedious to do lah. So I will just quickly show, but again this one for your knowledge only. So I just show the first few steps, then you want to try later on, you can try at home. So I will provide that step here. So what you need to do here is based on here, what you need to do, you estimate the model, and then you get a residual, and then you regress the residual. Let's say you assume a R1 process, so you regress the residual against leg 1 of residual to get the estimate of rho, and then you use that rho to estimate GLS equation, to estimate GLS regression, and then after that, after you get the estimate of coefficient here, you use the estimated coefficient here to recalculate the residual, and then use the calculated residual to estimate again the rho, and then you do that iteratively. So you do it iteratively. So the previous steps are depicted until further iteration result in interchange in estimated rho. We say it has converged. So this procedure involves substituting the values of parameter in step 3 into the iteration step 1. So I just quickly show the first few steps. I will not show you because time consuming. It is tedious and time consuming, but you can do at home later on. So basically, we will do the process. We will do the step until we get the value of estimate of row. There is a little change, so we will stop when the estimate of row there is no significant change in the value of estimate. Okay, so we repeat the process until we get the estimate of row. Until you identify or you realize that there is not much change if you keep further the process. I mean the change is very small, then you can stop. Okay, and then use that to estimate your GLS regression. Okay, GLS regression that gives us the reliable estimate of standard error. Okay. So for this one, we estimate the model. Again, this one just for your knowledge, not optional. I will not ask you to do. I will not ask you to do the test or even exam. Just for the additional knowledge now. Because later I will show you alternative way, easier way. You can get the estimate using reviews. You can easily get the estimate using reviews instead of using all this to do it manually step by step. So what we need to do first, you need to estimate the model. Okay, estimate the first model, and then we get the residual U. So the first residual, and then we which one? Previously we already estimate this one residual. And I will get so this one, this. So we save the residual as U, and then we estimate U against let one of U. To get that to give us the estimate of row. Oh, this one without C. This one without C. Okay. Okay. So this gives us an estimate of row 0.63, and then we use this to estimate the GLS just like before, GLS. But that one is not the final one, it's not the final GLS regression. So we use that to estimate our GLS regression as given here. And then we get estimate value of the intercept beta 0, beta 1, and beta 2. Beta 1 hat, beta 2 hat. And then we use that estimated value. We use the estimated value to generate new residuals. Okay. From here, after we estimate, we get the estimate. We get the estimate of the parameters, and we use the parameters to recalculate the residual. So now we generate new residual U1, which is using the estimated coefficient. So remember, so the residual U equal to Y minus the other parts. Okay. So we generate a new one. So we go to the quick generate series. Now we calculate a new error, new residual. So U1 using the estimated coefficient now. Okay. And then we continue the process by using the U1, the new calculator. So this one, so we estimate again. We repeat the process by estimating U1 and then space U1 let 1 to get new row. So we get now 0.67, and then we continue. So this one 0.67, and then we estimate get as equation, and then we use that to recalculate new residual. So until in the end we specify that there's only small change in the estimate of row. So maybe 0.68. This one, the next step 0.68 something. So not much different. And we stop. So it provides us more accurate estimate of rho lah. Instead of simply set into one or using the universal statistic to estimate the value of rho. Okay. But again, this one just acknowledge because now we have statistical software. Use can help us to easily get estimate. So we can use, for example, this one you can try. You want to continue to do the step, and then you can do. So the alternative way, basically we can. So this one eventually we just stop here because the value not much different. There's no small change. So we can just use this value to estimate our GLS equation, and then we use that GLS equation to form or to decide or to conduct harvest testing. Okay, whether you can say x1 and x2 significantly equals the dependent variable or not. We will set around 2.1. Okay, 2.12. For this one, if you use this one, then you get other slightly different values. The final estimate of rho. Or you can get this value of estimate using EBU easily. Okay, you go to after you estimate the original model Q1, equation 1, this one, the original model. When you estimate it, when you estimate the model, you add in R1. So the original model, you have y space x1 space x2. You just add one more in R1, assuming that there is in R1 the first order autocorrelation. So you just add in R1. And then you go to option. The method is like CLS. And then this one, you use legacy. The one of the option available, you can use this one to get estimate, just like how the current occur produced. Okay, so this one, change to CLS, change to image legacy. It's okay, so you get your rho 0.6862. Okay, and then you can use that to calculate your GLS regression. Okay, so you calculate your estimate, you get regression, get this one. Okay, so this one, you estimate the GLS regression, so you get this one. So you perform the test again. So it is free from autocorrelation. So you will see that it passed the F test, and then we must test it also to 2.12. You understand? So this one for the current marker is optional. I mentioned because now it is tedious to do. So now because you have the views that we can easily get estimates. So why do we need to use this one? The current marker. So we just use it. Okay. Other revenue measures, consider for possible regression of the model. The first other possible approach by using a different functional form, for example, using double log model. But this one you cannot use double log model because the variables consist of negative values, so you cannot. So let's say, for example, we estimate the model log y. The one because you cannot use this one because it has a negative. You cannot. I just want to show an example. Let's say one of possible approach is that you can try to use different functional form. So instead of linear, you use double log model, for example. But this one it won't work. It will not produce. It cannot be used because it has negative values. Negative values, so you cannot apply log. Okay, so we have to consider the approach. Okay, so this one, second one, the inclusion of additional variable. Inclusion of additional explanatory variable. So one of the variable that you can include because normally I mean, because data times is normally because the data is increasing. So if that's the case, then we can try to include time trend variables. So let's say y space c space x1 space x2 and then time trend. Trend plus 1. Okay, so now we will set 1.88 original value 0.59, remember that one. So whether or not we can use this size t and p value, so you have to test. So you go to view, residual diagnostic, see the correlation and test. Let's say the report number 2. So now this is p value 0.36. Okay lah. Okay. Next, the inclusion of lag variable, independent variable. Lag of the independent variable. So we estimate by adding lag of y. Y lag 1. Okay, so we will set 2.03. So you test again. By this one, the viewer set, I mean the value you can use, but you cannot compare the value to the critical value from table. Why you cannot compare to the DLCD from table? Because we have lag of y. Remember, the table, the DL and U, it produce is valid for the case of model without lag of y as our independent variable. But now we have y, lag of y as independent variable. So the L and U given by table is no longer valid for the model. So although the universal statistic can be used to give an idea whether the model is okay or not, because we need the value to be around 2, but you cannot it's not valid anymore to compare this value with the DLD from table, because we have lag 1 of the dependent variable. Yeah. But you can use an M test. You residual, see the correction M test. This one, okay. 0.05, okay lah, slightly lepas ke 0.05. Okay. And the last one, the use of robust standard error, the use of heteroscedasticity and automatic persistent covariant HAC. Similar to the previous lecture, we used we also have one option, but remember this one, if you want to do robust standard error, it can only be used when you have last sample size. For our example, we only have 20, so basically we're not really able to use that one. Sample size we have 20. So we need to have, I mentioned before, try to have at least 50 or 40 something, okay lah. And then you can use the robust standard error. So in order to use this one, you need to, when you estimate the model, you estimate individuals, but you go to option, it's like okay. Heteroscedasticity and autocorrelation. consistent covariance estimator. This I just show you example. So basically you should not do this for this given data because we only have 20 observations. Yeah. So in real practice, you want to use this approach, then you have to make sure you have sufficient large enough data. Yeah.
学习很奇怪，我就是不能在很长环境下学，就比如说老师讲课，我重点听进去，但不太想休息。
Because the problem of using this, we are not able to check whether it is free. After we estimate it is free from auto question mark, so we are able to check. Unlike the other approach, we can perform the test and see. Okay. So this one we estimate this one using HSC. Okay lah. So the numeracy still remains same. Estimate is still same. So if you have large enough sample size, then we can only trust. But this one we cannot trust because only 20 observation. Alright. So there is a number of ways that we can use in order to reduce or remedy the problems of correction in order to provide us a more reliable estimate of standard error, and then so that it gives us a more reliable result of hypothesis testing. Okay, hypothesis testing in order to say or in order to identify or to examine whether each of the independent variable significantly improves the dependent variable. Okay, so we have exercise that one we do after break. So we take half an hour break. We continue 5 minutes. Okay. Okay.
休息吧。